Exponential growth. Our exponential growth model is I of t equals I0 e to the RE times t. I0 is the initial infected population, and RE is the exponential growth rate. This E is a subscript, stands for exponential. T is time. This could be any time unit, but days is usually appropriate with the spread of a virus. And I of t is the number infected at time t. So for instance, suppose on January 10th we have 20 infections, and on January 15th we have 40. So every 5 days it looks like the infection is doubling. Set up an exponential model. Well, first of all, we need to identify this parameter. I0 is 20. So we're going to substitute that into our model. I of t is 20 e to the RE times t. And then next we need another data point to establish what RE is. And that comes into play right here. From the 10th to the 15th, 15 minus 10 is 5 days. So when t equals 5 days, I is equal to 40 infections. So we can substitute 40 here, 5 here, and we get 40 equals 20 e to the RE times 5. And then we can divide by 20. Let's bring it up here, and we get 2 equals, here 20 cancels, e to the, you can switch this around if you want. And then we're going to cancel out e by taking the natural log of both sides. Natural log of 2, natural log e to the 5 RE. That cancels. ln2 is equal to 5 RE. Divide by 5. RE is ln2 divided by 5. And we can approximate that on our calculator. Now we end up with 0.139. That's the 3 sig figs. It's 1386, but we can round it to 9. And so we have I of t is equal to, we can plug it back in here, 20 e to the 0.139 t. And there's our exponential model right there. Okay, that was our goal. In a subsequent video, we'll learn how to work with this. You can either plug in t and solve for the number of infections, or you can plug in the number of infections and solve for time t. So those are all good pre-calculus skills that we're interested in. So that's all for this video.